Hello and welcome everyone to non-IITN, and if you are enjoying the content, please don't forget to like, share and subscribe. So in this video we are going to talk about a problem which had come in NBHM PhD 2019, and the question was on complex analysis, in which we were to analyze three statements whether they were true or not, and the questions were as follows. The statements were as follows. There exists an analytic function f from C to C such that its real part is e to the power x, where z is equals to x plus I y. Okay. There exists an analytic function f from C to C such that f of z is equal to z for all z on the boundary of the unit circle, and is z square for all z on the boundary of the circle centered at origin and radius 2. And the third statement is that there exists an analytic function f from C to C such that when f of 0 is 1, f of 4i is I, and for all zj such that 1 is less than zj is less than 1 is less than mod of zj is less than 3, j is equals to 1 to 2, we have modulus of f of z1 minus f of z2 less than or equal to mod of z1 minus z2 to the power pi over 3. Fine. Let's try and analyze each of the statements. Okay. So this is the analysis of statement 1. So we are given a function f from C to C, which is analytic, and the real part of f is e to the power x. Now there is a very standard result in complex analysis which says that if, so let me just frame it out. So if f from some domain D to C is analytic, and I can write f as u plus iv, where u is a function from R2 to R, v is a function from R2 to R. These are the real and the imaginary parts of the function. Then u and v are harmonic functions. Okay, that is uxx plus uyy is equal to 0 and vxx plus vyy is equal to 0. In fact, u and v are called harmonic conjugates. Okay, so the proof of this statement, it immediately follows from the fact that once a function is holomorphic, it's smooth, that it's infinitely differentiable. So every partial derivative of both u and v exists, and these CR equations. Okay, why did I specify the fact that every partial derivative of u and v exists? Because from the CR equations this can be proved, but in that case you require interchanging the order of the partial derivatives, for which you need continuity, and the continuity is guaranteed from the function that from the concept that the function is smooth, that it's infinitely differentiable. Nevertheless, this is the fact we require. Now I am given u is e to the power x, right? Therefore, what is the partial derivative of u with respect to x? It's e to the power x. What is the second partial derivative with respect to x? It's still e to the power x. And I have partial derivative of u with respect to y to be 0. So my uyy is also 0. But then we know, uxx plus uyy, which is equal to e to the power x, this is never 0 for any x, right? Therefore the function u is not harmonic. U is not harmonic, and so it will contradict analyticity of f. So therefore such an analytic function whose real part is e to the power x cannot exist, contradicts the analyticity of f. Okay, so the first statement is false. Okay, so let me just specify this here. So this is a false statement. Now what was the second statement? There exists an analytic function which is z on mod z equal to 1 and z squared on mod z equal to 2. But then this is also a very, okay, so I have written the conclusion here, it's not harmonic, so it cannot be the real part of any analytic function, right? Now let us come to the analysis of statement B. So we are given f, a function from C to C, which is entire or analytic, and f of z is equals to z on mod z equal to 1 and f of z equals to z squared on mod z equals to 2. Okay, let us try and prove this, that this is not possible. And if you know, so I have already written it, that this is an easy application of the identity theorem. So let us just go to it. And the identity theorem basically speaks the fact, so let me just use it in a very layman tone. If f equals to g on a set which has limit points in C, then f is identically equal to g on D, where D is the whole domain. Okay, is it clear? And this actually follows from the fact that I can choose a function h equal to f minus g, then h will be equal to 0 on a set having limit points. And then I can apply the identity theorem to claim that h is identically 0 on the domain, and then hence f is identically equal to g on the whole domain. Okay, and here we have the domain to be equal to C, to be very specific. Now observe that, so I can immediately claim it from here. Now since f of z equals to z on the unit circle, and obviously the unit circle admits limit points on C, so f of z should be equal to z on the whole of C, and hence f of z cannot be equal to z square on mod of z is equal to 2. Clear? Because if f of z equal to z square, then what does that mean? Z equal to z square, then you can just analyze the values, what will z eventually bring out from here, right? See, there are algebraic properties of C which says that C is an integral domain. So my z, so z times z minus 1 must be equal to 0. So my z should be either 0 or z should be 1. These are the only possibilities. So this is not possible on mod z equal to 2. That something which we can immediately see. I hope it's clear, right? So this is an easy application of the identity theorem. Is it clear? Okay. So the two conditions are contradictory. No such analytic function can exist. So statement B is false. Now let us come to statement C, and this is in fact the most interesting statement which we have. So here what I had was a function f from C to C which was analytic, and what were the conditions? I just forgot. So the conditions were, let me just go back once. So I had f at 0 to be 1, f at 4i to be I. Okay, so let me just come back. So f at 0 was 1, f of 4i was I, and for all 1 less than mod zj less than 3 with j is equals to 1 or 2, I had mod of f of z1 minus f of z2 is less than equals to mod of z1 minus z2 to the power pi over 3. Okay, so this was what was given to us. Fine. Okay, now let's try and analyze this concept. Okay, so where does these zj's belong? So if I just simply draw it out once, okay, so these zj's belong to the following place. So it's actually, so this is my unit circle, and this is the circle around origin of radius 3. Okay, so my zj is basically here. My zj's come from this annular region. Okay, and this annular region is a connected set. It's clearly visible to be an open set. Okay, so it's a domain, it's a connected domain, and you need to be very specific about the word connected. Okay, and we'll see why. Okay, now we are given this. Now, so what can I say about mod of f of z1 minus z2 divided by z1 minus z2 under modulus? So this should be less than or equals to mod of z1 minus z2 pi by 3 minus 1, which is nothing but mod of z1 minus z2 pi minus 3 by 3. But we know that pi is slightly bigger than 3, right? So this particular thing, this is greater than 1, right? So this is greater than 1. Therefore, what is limit z1 goes to z2 of f of z1 minus f of z2 divided by z1 minus z2, that should be less than or equals to, by the algebra of limits, limit z1 goes to z2, limit z1 minus z2 to the power, let's say alpha is greater than 1, and sorry, not greater than 1, it's greater than 0. I'm extremely sorry, it's greater than 0. Okay, and so this becomes 0, right? So therefore this means that modulus of f prime at z1 is equal to 0 for every 1 less than mod of z1 is less than 3. So I can just write it as f prime at z, okay, because z1 and z2 were arbitrarily chosen. So what does this imply? This implies that f prime of z is equal to 0 on the annular region as stated above, right? And the annular region is connected. So recall that if f prime of z is equal to 0 for all z over a connected set, so the requirement of a connected set is required, then f is a constant function. We require it to be a connected set, okay, because let me just say you this in very subtle way. You can choose a domain like this, okay, a ball here, a ball here, then the derivative you can define f to be, let's say, 1 here minus 1 here, and if you calculate the derivative of f, it will come out to be 0. But f is not constant, right? F is constant locally, but f is not constant on the whole domain if you consider this to be domain. And observe, this is not a connected set. So since this is connected, what can I conclude? So this implies that my f of z is equals to c for some c, that is f is constant. But once we have this, f cannot choose two different values at two different points because f is a constant function, right? So this contradicts the fact that f of 0 is equal to 1 and f of 4i is equals to I. So therefore the conditions are again contradictory, so no such analytic functions can exist, and hence statement C is also false. Final conclusions. The final answer, none of the statements are true. Clear? Thank you for watching. Please like, share and subscribe to Non-IITian.